So, hi everyone. So, today I'll discuss a very interesting topic, how we can tame large language models. It's also known as alignment. Another very common name for it is reinforcement learning with human feedback. We learn why. As you know, I share all my slides also in PowerPoint format. You just need to go to my GitHub website and just go to talks. Okay, so let's ask a question. What do we want from large language models? Do we want them to be helpful? The answer is for sure. We want them to be helpful, but is that all that we want? So the answer is no. We want much more than that. We want them to understand human values. We want them to understand human ethics, legalities of different things. We want them to understand humor and a lot more. So, for example, if you ask an LLM to give you a recipe of some illegal drug, if it's only being helpful, it will give you the recipe. But that's not what we want from them. We want them to be even more cautious when you are dealing with a young child or a kid. So this is where alignment comes into play. So what is alignment? Alignment, on top of what large language models have already learned, alignment is what teaches the model to act in a safe manner that we expect from it. We, as I said, we want it to be ethical. We want it to even be funny at times, right? So everything that humans care about, we want the model to learn. And how is this possible? That is only possible by human feedback. We know what we want. So by crowdsourcing, we can tell the model and we can teach it enough so that it behaves in a way that is very close to how human would behave in a situation. Is there a perfect solution? No, there is none perfect solution. We see many problems with different models, but for now, this is the best method available for us to align these large language models. So, reinforcement learning with human feedback. Let me go to reinforcement learning first. What is reinforcement learning? So, reinforcement learning is learning from some kind of signal from an environment. It's inspired by how humans learn, how children learn. Especially, an example is when a child learns to walk or ride a bicycle. The only signal they get is, after many action, the only signal they get is whether they fall or not, right? And based on that signal, the muscles over time learn what action should I perform so that I get a higher reward. I go where I need to go instead of falling. So in reinforcement learning, what we have is, we have an agent. Let's call it a policy pi that we want to learn. It's parameterized on theta. So theta are the parameters that we want to learn. And the agent can interact with the environment during learning also. It performs an action on the environment, it gets back the next state of the environment, and it gets some kind of reward. The reward can be very dense, like the environment can return a reward in each step, or it can be very sparse. As I said, like after many actions, it can just give you one reward. So from this very weak signal, the agent ends up learning what it needs to do. So what is the difference between supervised fine-tuning versus RLHF? This is just intuitive explanation. I'm not going into any technical detail on this slide. But how we should think, why supervised fine-tuning is not enough. I'll go through the stages of training large language models and why it's not enough. To me, supervised fine-tuning is like learning from documents, from books, from websites, from a lot of text that is available, from question answer pair. Okay, we don't allow the model to ask questions in case of pure supervised fine tuning. In case of reinforcement learning with human feedback, we allow the large language model to ask questions. Okay, it can generate something, and the teacher or an annotator or a user can get feedback, whether the outcome is good or bad, which outcome is good, which outcome is bad. So that's a big difference. So supervised fine tuning is one way, uh, RLHF is two way. Again, this is not a technical slide, this is just intuitive explanation. So let me briefly discuss different types of reinforcement learning. On policy versus off policy. In on policy, we sample from the current policy that we are training. Because the current policy is always moving, we are training that policy, so that's why it can take longer to converge. Off policy is where we use a different policy. It can be some version of the same policy that we are training, and we keep an experience replay buffer um, to train our policy. In online versus offline, in online we are actively sampling, creating new data, and we are training based on that. In offline, we are given a data set, and we just use that given data set to learn the value function or the policy directly. In value versus gradient, what we are doing in value based method, we are trying to estimate how good the current state is, and how much expected cumulative reward can we get from going from current state to the final desired state where we want to go. Okay. In policy gradient method, we directly optimize the policy that we want to run. Like a policy is simply a network where we give some state and we expect the action, it will output the action. Okay, so this is some um, types of RL from different perspectives. So reinforcement learning with human feedback. So in normal reinforcement learning cases, let's suppose you are teaching a model to learn an Atari game, the reward comes from the environment, the reward does not come from a human feedback. But this started around, experimentation started around 2017, where different people started to look at how we can add human feedback in the process. So reinforcement learning algorithm is performing an action on the environment and then getting an observation back, and in order to get the reward, it's getting it through human feedback. It's not always possible to give human feedback for every single step. So how we make it very efficient, I'll show in the next slides. But so here I'm showing an early attempt to reinforcement learning with human feedback from September 2020. The idea is very straightforward, it's easy to understand. So we have like any pair of, let's suppose, a query and few responses, and the human judges which one is better. And based on this data, we call this kind of data preference data. So based on this kind of preference data, we create a reward model. Reward model just tells us how good or bad the output is given the query or the question, and we use that to ultimately train the PPO policy or the reinforcement learning policy. I'll go into much more detail, so if you don't understand exactly, don't worry. This is where reinforcement learning with human feedback goes mainstream. So the paper on Instruct GPT was published in March 2022, and then later, as we know, ChatGPT was released around November 2022, and ChatGPT also uses the same method that they use for Instruct GPT. I'll show that into more detail in the next slide. And this is where it got really mainstream, and it's being used very commonly now by most of the models that are trained and made available to us. how does RLHF model compares with base model, that is pre-trained, or a SFT model, which is supervised fine-tuned? So in this figure you can see that a PPO or PPO with regularization, KL regularization, perform much better. Even smaller models perform much better than supervised fine-tuned models that are much bigger in size. So that's the power of reinforcement learning with human feedback, because it can incorporate human preferences much better than what supervised fine-tuned and pre-trained models can do. So I would like to go a bit more in detail on this slide. This is taken from the Instruct GPT paper. You can see in step 1, what we do is collect demonstration data and train a supervised policy. Here what we have is we have a pair of a query or instruction and the response. Okay, for example, you can have many queries from some kind of data set, like explain the moon landing to a 6-year-old, and the demonstrator basically assigns the output to the question, and using this question and response pair, the supervised fine-tuning policy is trained. In step 2, so now supervised fine-tuning is done in step 1. In step 2, what we are interested in is training a reward model. In reward model, we take some prompts from some data set. We ask the model to generate multiple outputs, A, B, C, D in this case. Then we ask a human labeler or annotator to just tell us which is better than the other. It's much easier for humans to tell which output is better compared to rating an output, like giving a number from, let's suppose, 0 to 10. Okay, so in this case we are just asking the human to tell us which output is better than the other. So in this case, D is better than C is better than A, and A or B are equal. We use this preference data to train a different model. This is not the main policy that we are interested in. This is a different model that we call reward model. Reward model is trained on huge quantities of this preference data. Okay. And in the last step, what we do is we use this reward model and we start from the SFT policy, and we use a reinforcement learning algorithm. In this case, we are using PPO algorithm, which is one of the most famous algorithms used in this language domain, to learn our policy, to train our policy as per the human preferences that are basically now represented in the reward model. So what happens in step 3 is we have again a prompt data set. Okay, it can be any data set that we want to use, and then we pass it through the policy. This PPO policy started as SFT policy, but now it's being iteratively updated as a result of PPO iterations. It generates some result, once upon a time something. Then the reward models tell us how good or bad it is. It produces a scalar reward, RK in this case, and then based on this we feed it back to the PPO policy and we update the parameters, and this goes on. So there are several steps in training a foundation model or a large language model. In step number 1, we do what we call pre-training. Pre-training is done on huge amounts of data, like hundreds of billions to trillions of tokens of data. And this is unlabeled data. This is crawled from the internet. This comes from the books. It comes from repositories, source code, a lot of stuff. This is what gives us the base model. After that, we perform supervised fine-tuning. It's also called instruction fine-tuning, so that now the model can understand our instructions. So this is usually done on 100k to a million instructions, okay, that are either human annotated or taken from some data sets. The last step is alignment, what I am trying to discuss here. um, Alignment is where we take some prompts, we let the model generate the output, and we rank it according to the reward model, and we feed it back to the training process in order for us to become the model becoming better at getting higher and higher reward. So with this basic introduction to RLHF, how do we train with RLHF or RLAIF? The difference between RLHF and RLAIF is that HF stands for human feedback and AI stands for AI feedback. So I'll show that later, but human feedback can be very expensive. On the other hand, in some cases, you can get the feedback from other large language models. This significantly reduces the amount of feedback that we need from human, and which can make the process much more cost effective and fast. So let me briefly explain what preference data is, how it looks like. This is a preference data called Anthropic HH RLHF data, which stands for helpful and harmless. Here in this highlighted example, you can see like we have a chosen response and we have a rejected response. Okay, so the chosen response is, given the question, how can I get my dog high? The assistant replies, I'm not sure what you mean by that. So this is chosen. And the rejected response by the human annotator is, for the same question, the assistant response is, I don't know what we should that we should get the dog high. I think it's important for dog to experience the world in sober state of mind. So now sometimes the chosen and rejected can both be good, but one is preferred over the other. Sometimes the chosen is really good and rejected is really bad. Okay, so but anyways, the human annotator preferred the chosen over the rejected ones here. Let me explain you how reward model is trained. So we start from a prompts data set. This is just a data set containing some sentence or some instructions. And then we pass it to an LLM. The LLM outputs possible answers. We sample it multiple times so it can give us multiple answers. So in this case, it gave 4 answers. We ask a human annotator in case of RLHF, or we use yet another large language model to label us in case of RLAIF. What we want them to label is which output is better than the other. So in this case, the human annotator decided that A is better than B, B is equal to D, and D is better than C. And then we create a large amount of this preference data set, and then we use this data set to train our reward model. So what this is trying to maximize is the expectation over this function that we'll discuss in the next slide. If we look at the bottom right figure, reward model, all it is doing is giving us a scalar value for an input and output pair. Okay, that's it. That's what we expect from the reward model. And just using this scalar value, we can feed it back to the PPO pipeline, and we can make our model learn. So let's look at the derivation of the reward model loss function. So we start with Bradley-Terry model. Bradley-Terry model tells us that if something is preferred over something else, what should be the relationship between their strengths. Okay, so in this case, we have given the input X, we have 2 outputs, the winner output YW and the loser output YL, and this curly greater than sign basically shows preference instead of a relation, like greater than relation. Okay, so And we just chose to use exponential function of the reward model on winner and reward model given input and loser to show the strength. So exponential function here shows the strength of different kind of inputs. And then it can be derived very easily into a sigmoid, and then we use log of the sigmoid for more stability, and then we use this, the last equation, as the loss function for training the reward model given x, yl, and yw. Okay, this is what we get from the preference data set. Okay, so now our reward model got trained. What can we do with it? So this is the simplest form of reinforcement learning that we can do using the reward model in our iteration. So there are a few steps. In step number 1, we take a large language model, we sample few outcomes. In number 2, we do rejection sampling, where we reject some of the generated output based on the reward that they got. And in step number 3, we perform supervised fine-tuning. This is just a supervised fine-tuning. There is no PPO, nothing, no RL algorithms. And then we repeat this process. Okay. And over time, the large language model generates many outputs. It gets to know which one is better, and it tries to, through supervised fine-tuning, it learns to generate the better outputs more often. And that is alignment. And we can take our aligned large language model after whatever number of iterations we are happy with. In the last slide, we saw how we can perform reinforcement learning using rejection sampling. However, that method is not very efficient. Okay, so we have to use some reinforcement learning algorithm in order to make it much more efficient and give some stability during the training process also. So the most commonly used algorithm in reinforcement learning in general, and especially in context of reinforcement learning with human feedback, is called proximal policy optimization. And why it's called proximal policy optimization, we'll see in this figure. So again, we have to start with the prompts data set. Prompt data set, the job is that given a prompt, like in this case, the input is an apple is, we give it to two different large language models. One is the reference large language model, and the other one is the large language model that we are training. Okay, both are parameterized. They both can start from the same supervised fine-tuned model, and usually they do start from the same model, and then of course one gets trained, the other one is kept frozen. What we do is, for both of these, we sample the output. Okay, for example, one of them can say an apple is a healthy fruit, the other one can say an apple is usually red. Then what we have to do is we pass it to the reward model. The reward model tells us how good or bad the outcome of the policy is, the current policy is. And that alone is not enough. Like just getting a signal on how good something is, that's not enough, because if we only train on that, the large language model will just learn to hack the reward model. It will just keep saying something very nice that the reward model likes, and ultimately the output will be useless. I'll show some examples later. So we add this term called KL divergence term. KL divergence term, what it does is that it tries to keep the policy that we want to train close to the reference policy. Okay. So now if you want to read it, you can read it like, we have the objective function which tries to maximize the reward given the reward model, but it forces it to, the KL divergence term forces it to stay as close as the reference policy as possible. Okay, so this is how you read it, and you maximize the expectation on this new big reward function now, which includes the KL divergence term. So as I said, so this is just a repetition because this is an important point. So we don't care about r phi r of x anymore alone. Okay, of course that's important, that's the reward, that's important, but we are also interested in this KL divergence term, which is telling the model not to deviate too much from the original parameters or the original policy that it started from, that we call pi ref in this case, or pi reference. Okay. And we don't have any closed form solution to solve this equation. We usually do it solving some reinforcement learning algorithm on the reward function that I have listed at the end of this, the big R x of y, which is again R, which is the reward from the reward model, minus the KL divergence term. What's the role of KL penalty? It will be very clear from this example. Okay, it's taken from this paper. Given the context, you see that if there is no penalty bonus, what it learns it these sound, it runs like strange words, it make up some words. Why it's doing that? Because somehow reward models loves those kind of terms, so it's just trying to maximize the reward, but it doesn't care about the naturalness or any other thing that the model has learned before. So it very quickly, without KL divergence term, it very quickly forgets what it has learned before, and it just learns to hack the reward model to maximize its reward. So I already discussed proximal policy optimization in the previous slides. Recently, some other methods have also started to appear. Direct preference optimization is one of them. It shows more stability, it's more scalable, and that's why it's becoming more common to use DPO or other such approaches as opposed to PPO. So in case of reinforcement learning with human feedback, if we look at the left part of the figure, we start with the preference data, we learn a reward model, and from this reward model we train the policy, final policy. In case of direct preference optimization, what we do is we directly learn from this preference data. We don't have a reward model here, and we just go to the final policy. Why it can do that? We just need to look at the title of the paper, which says DPO, your language model is secretly a reward model. Okay, so you can check the paper for the full derivation of their loss function. What they are saying is that the reward is implicitly defined by the language model, and this is how it is represented. Beta is a constant, and then log of pi theta, this is the policy that we are learning, and pi ref is the policy that we have frozen. This is a reference policy, as I discussed in the context of KL divergence earlier also. So taking the gradient with respect to the parameters theta, we reach this function. This is what will be optimized. What it is trying to say is that higher weight when reward estimate is wrong. So if the reward estimates that are computed are wrong basically from what it should be, then this becomes higher. And this term is just saying increase the likelihood of the good outcome and decrease the likelihood of bad outcome. So YL, YW, if you remember, YW is the winner, YL is the loser in this case. So let me show you an example of Llama 2 chat alignment. So how Llama 2 was trained. So if you look at the figure, it's trained on human preference data, and then it has two reward models, helpful reward model and safety reward model. Because we want it to be helpful, we want it to be safe at the same time. Okay, and then it does rejection sampling, it does PPO, and then we get the new version of the Llama 2 chat, and then they kept iterating several times to get, and then where they got the first Llama 2 chat model was through pre-training and then performing supervised fine-tuning on top of it, and they got the Llama 2 chat. Okay. What they did is they did some rejection sampling, and they did non-PPO approach and PPO approach, and we can see in this plot what they show is on helpfulness meta reward model, like the judge is meta reward model, and here, which is more interesting, the judge is GPT-4. GPT-4 is just telling which outcome is better, which outcome is worse. Okay, so here what we see is that their supervised fine-tuning version 1 was here in helpfulness and harmlessness, and then it kept improving and improving, and then they did RLHF v2, RLHF v3, v1, v4. All these are done using non-PPO approach, which means rejection sampling, supervised fine-tuning, rejection sampling, supervised fine-tuning. This is the last stage done without PPO. This is the last stage done with PPO. So they saw that in the last stage, if they do PPO, they get much bigger jump than if they don't do PPO. This is a practical example of using PPO or RLHF and how it can benefit in different dimensions, which they care about, in this case helpfulness and harmlessness. Okay, so just to explain like that, reinforcement learning with human feedback is not cheap. Okay, you need an army of annotators given the outputs from LLM, in this case let's suppose A, B, usually there are multiple these like model like ChatGPT and Claude, they are trained by armies of annotators annotating continuously their outcomes. This can be very costly and it's not very scalable. So what can we do about it? So we can do RLAIF, where we use a judge large language model to give us the preference where it's very, very obvious, and we still keep small number of human annotators who can annotate difficult cases for us. So with this combination of LLM as a judge and human annotators, we can do the whole process much more scalably and with a lot less cost. However, we need to understand that the judge LLM was trained maybe with a huge number of annotators. So the judge LLM needs to be strong in order for this to be a viable solution. So summary, alignment is a key step in training of instruction following chatbots like ChatGPT, like Gemini, like Llama, Claude. So it's a way to kind of like whatever the model is learning from pre-training, supervised fine-tuning, it's a way to give a lot more information that comes from the preference data. So a good quality preference data is a key here to making a good reward model. Good reward model is a key to training, better training the final policy. PPO is the default approach to do alignment with RL. However, non-PPO approaches like DPO are getting traction because of their simplicity and stability. Okay, so thank you. There are many ways to connect with me. You can see some links here. Feel free to connect with me. If you want to download the PowerPoint, fully editable PowerPoint slides of this talk, you can go to my GitHub page and just go to talks. Thank you.